ಓಕೆ ದೇವರಾಜ್ ಶುರು ಮಾಡೋಣ.
ಆಯ್ತು ಸರ್.
ಹಾ ಸರ್.
ನಮಸ್ಕಾರ ಸರ್.
How are you?
I'm good, sir. Thank you.
Yes,
How are
right.
you?
Okay, okay. Thank you. We'll continue. Right.
Yeah.
Yeah. So I welcome today's afternoon speaker, Dr. Devaraju Narayanappa, who is working in Department of Geosciences, University of Oslo, Norway. I request my colleague, Dr. M.S. Basuraj, to introduce him.
Okay, good afternoon, everyone. I welcome you all for the post-lunch session. Now I would like to introduce today's speaker, Dr. Devaraju Narayanappa. He obtained his PhD degree from Bangalore University in the year 2009. He obtained a postdoctoral degree from Indian Institute of Science, Bangalore in the year 2012. He worked as a project scientist at the AAC during 2012 to 2015. And he worked as a scientific researcher at LSCE France during 2015 to 2020. Currently, he is working as a postdoctoral researcher at the University of Oslo, Norway. He has got many awards. He received CNRS Grant Award for the participation in European research course on atmospheres in Grenoble, France, during January to February 2011, and he guided 2 PhD students. He published many reputed journals, international and national journals, and he, with this, I request Dr. Devaraj Narayanappa to deliver a talk on mathematical model for predicting climate. Okay.
Yeah, thank you for the introduction. And thanks to the head of the department for the invitation, actually. So just one clarification, is the participants are all physically present or is all over Zoom?
Yeah, they are present not physically, they are present online, not in the Zoom, they are in the YouTube. So they will not interact with you directly, only they can pose the questions to us, intern will ask you the questions if at all they post.
Okay, yeah. So, yeah, that's good to know, thanks. Okay, so the topic of my presentation today is mathematical models for prediction of climate. I hope to introduce some basic models like equations to predict the climate, and also the complex models. So I'll start with some basic models, and then maybe into another session, the next session, so I'll go with the complex like global climate models. Okay, can you see the next slide? Yeah, okay. So this is the outline of my talk. So I'll give first some brief introduction to the climate, and then simple mathematical models for predicting the climate, and then complex models, and then I'll also show some real-world applications of these climate models, and then I'll end with some takeaway messages. Probably in the first session, I'll try to focus on these two, that is introduction and then simple mathematical models. And I also see that the participants are introduced to Python programming. Maybe I'll try to give some one exercise to do to solve the mathematical equation for predicting the DOC concentrations or climate variables, if that is possible. Okay, then so that's the introduction. So I think it's important to know what is exactly the climate, or what is the difference between weather and climate. So today what I'm talking about is mostly the climate. So climate means it's the average weather conditions of a place, usually measured over a long period of time. So that is from months to thousands of years or millions years. So let's say you say that, oh, this winter or the next winter is going to be warmer, or the last winter it is like much colder. So if you say like winter, that means like 3 months, more than a month. If you say, then that is a climate. Or if you say like, oh, this next few days, it's going to be like warming or raining. So then that is a weather actually. So that's the main difference. So if you see that the weather, it's short-term state of the atmosphere, like the temperature or rainfall changes within minutes or hours or even days. So then that you refer to weather. And sorry, for the climate means it's a long-term pattern of weather. So for example, in tropical climate, this is a figure. You see that the temperature versus time. So it's like average weather over many years in one specific place or even global temperature. So if you want to say that, or in some specific place, if you take average of like 3 months or a year, like 100 years or 1,000 years, then you call that as a climate. Whereas only for shorter time, it is weather. So how do we develop the mathematical models to predict the climate? So yeah, if you just look at the Earth, actually it is really complex. So you have a land surface, and then you have oceans, you have snow, mountains, forest, and there is an interaction of the Earth land surface or trees with the atmosphere, even oceans with the atmosphere. So you have an exchange of energy between atmosphere and ocean, exchange of water between atmosphere and ocean. So this is really complex. How do we really predict the climate? So climate means like basically we can say like either temperature or precipitation, which is most commonly referred variables are temperature and rainfall. Rainfall is also known as like precipitation in some cases. Nowadays, the climate models are evolving and they're just climate. So if you include some of the only processes like shown in this schematic, if you see some runoff, infiltration, soil water, groundwater, subsurface drainage, or just the trees, and if you represent in a mathematical equations for this, so this schematic, then it is climate model. And if you have like the present day or next generation climate models are trying to include like deforestation, afforestation, agriculture practices, dynamic vegetation, like different kinds of emissions like CO2, methane, chemistry aerosols, wetlands. So if you want to really predict accurately the climate, that means you need to develop the models to represent the almost entire processes exist on the Earth. So the next generation Earth system models are really trying to represent all these processes through mathematical models. Then we can really predict the climate, more accurately. So basically, so the mathematical models to predict climate means you need to represent the equations, like you need to write equations to represent the whole Earth system. So yeah, just a quick schematic to show, okay, this is the like real world problem you have. Convert the real world problem into mathematical equations. And then in mathematics world, we see that globe in a square box with different grid cells. Okay, so that is you discretize the equations and solve or manipulate, identify the variables, and then so run or like run those equations or programs using computers, and then examine and predict the real world problem. And then so basically you represent the real world problem through equations, real world problem to the equations and then try to replicate the climate. So as I showed in the previous figure, the prediction of climate change induced by anthropogenic process. So anthropogenic process means emissions, CO2 here. So you have see the greenhouse gases emissions due to the human, like from after the industrial era. So you started emitting the CO2 or started disturbing the climate or natural ecosystem. Then that is anthropogenic processes. So the prediction of the climate change induced by this anthropogenic process is one of the most important challenges for science in the 21st century. Yeah, just to give a brief state of the climate system. So the climate system is characterized by a set of distributed parameters like temperature and precipitation. Rain, the main difference between precipitation and rain means precipitation includes also snowfall, like rain plus snow is called precipitation. And the pressure, humidity, velocity of wind in the atmosphere, and of currents in the ocean, like CO2 concentrations or methane concentrations, NO2 like nitrous oxide emissions. So it all includes the climate system. Okay, so next, how do we represent the whole system in simple mathematical equations? So I'll start with some basic equations like zero-dimensional mathematical models and go on with the complex models. So yeah, this is the schematic for the Earth. So let's say you have incoming, this is the energy coming from the sun, solar, and which is going and it reflects, the energy reflects back to the atmosphere. So I think way back from more than 50 years or 60 years ago, scientists started to write an equations for this process. So let's say the whole Earth system, you do not have atmosphere, you just assume that it's like a block body. And then, so whatever the incoming radiation is equal to the outgoing radiation. So this is what here, these equations represent. The incoming radiation is equal to the emission of, this is the, according to Stefan Boltzmann law, that is gamma sigma T to the temperature to the power 4. So this is the emission from the block body from the Earth. Let's say you assume that you do not have any atmosphere, so it's just on a block body. So that means whatever receiving from the sun, the radiation, which is all going back. So that means it's a balance of energy. So yeah, so this is the equation. And from this equation, you can predict the temperature, find the temperature. So that is the effective temperature can be defined by writing down the radiation balance equation for the whole system. I mean, this is just a big assumption. And so that it just assume that there is no atmosphere, no interactions, with the atmosphere, the radiation, there is no interaction from the radiation with the atmosphere. Then this equation represents a simple radiation balance model. And from this, you can calculate the temperature. Okay, so yeah, where IE is the integral flux of solar radiation, and alpha is the effective albedo of the climate system, and gamma is the grayness coefficient, and T is the effective temperature. Okay. Next, slightly higher version of the model, so more try to include more processes now. So this is a one-dimensional model. Yeah, this one-dimensional model includes the radiation model and radiation convection models. The rate of change in temperature. So rate of change in temperature along the vertical coordinates. Let's say along the vertical direction Z is equal to the radiative flux, heat fluxes distributing along the Z is the vertical coordinate. So here epsilon of Z denotes the radiative heat fluxes distributed along the vertical coordinate. So let's say you have some radiation interaction with along the vertical direction in the atmosphere, then you include the radiative heat fluxes, how the convection occurs, the radiation convection representation. So you can include this process instead of just assuming like in the previous equation, you just assume whatever the radiation. So here, whatever is coming in, which is going out, so that's the radiation balance. And here, but we are trying to include the convection process in this equation. So in the case of radiation convection models, it also accounts for the vertical mixing by the mechanism of effective convection. So this is the process that included in this equation. So yeah, after certain closure procedure of the heavy heat fluxes, the heat transport equation takes the form. So yeah, this is the equation from this paper I have obtained. Basically this equation in vertical coordinates, spherical coordinates. Yeah, so this is an one-dimensional mathematical model. Again, from this, you can find the solution for temperature and predict the temperature. So here we are not including the precipitation or other terms. This is a simple model to predict the temperature. Okay, so let's go to another slightly higher version again. So on the surface of the Earth, so let's develop or write an equation for the energy budget. So again, so in a hypothetical, I'll just remind that in a hypothetical situation, like there is no radiation process, no feedbacks in the atmosphere, just whatever is incoming radiation from the sun is going out, okay, is equal to 0. So that's what then the first zero-dimensional equation I showed. So this is the equation for hypothetical situation. So, but when you have the atmosphere, let's go back. Yeah, with the clouds and also that means, so the radiation while going back, so if there are clouds, then you have interaction. It's not everything goes back. So there will be interaction and feedbacks with the within the atmosphere. So to include that means, so yeah, if there is a reflection, so that means you have like sensible heat fluxes on the surface. Let's say if it is for a real atmosphere, if you want, then it's not like a black body, everything does not go back. So you have an interaction. So soil gets warmed up. So that means you have like Earth's surface is getting warmed and the heat is distributed along the atmosphere. That means like you have a sensible heat flux, that is latent heat flux. That means you have water evaporation from the surface. So that evaporation also transport energy into the atmosphere, and you have also ground heat flux. So that means whatever incoming radiation minus outgoing radiation is not 0, but it is distributed in terms of like sensible heat, latent heat flux, and ground heat flux. So again, this is a energy balance equation. So yeah, so if there is any difference, it should be always to balance the equation. So this is what incoming minus outgoing is 0. But because of the real atmosphere, so this should, to balance this, so you have the energy which is coming in and which is distributed over to the atmosphere in terms of sensible heat and latent heat, ground heat. So again, this is another model for surface energy budget equation, and then again you can calculate the surface temperature from this equation. It's a, yeah, again you can calculate one of the climate variable, that is temperature, and you can also calculate the air temperature through sensible heat flux actually. But yeah, I'll go into details of the formulas for sensible heat and latent heat later on. In most of the models, usually ground heat flux are assumed as like negligible, but so these two are important, sensible and latent heat flux. Yeah, so this is the model for sensible and latent heat fluxes. Like how do you calculate? So the sensible and latent heat fluxes are also called as turbulent fluxes. So if you assume this is the like Earth surface, you have like surface temperature and you have air temperature. Let's say you have a 2 meter height from the surface, from the Earth surface to the atmosphere, like 2 meter, let's say. So then the sensible heat flux definition is nothing but this. So that is the difference between air temperature, that is TA minus TS, and with the resistance. So you have the resistance term here, and this is the sensible heat flux formula. And similarly for the latent heat flux, you have the conductivity. So the here the bulk model, sorry. Yeah, the aerodynamic conductance is this. Aerodynamic conductance, like how much the water, like conductance for water transpiration, water evaporation, sorry. So again, this is vapor pressure deficit at the vapor pressure at the surface and at the like 2 meter height in the atmosphere. So the formula is here for the latent heat flux. So yeah, this is how you try to include now more processes in the atmosphere in all the equations to represent the mathematical model to predict the surface temperature. Yeah. So that means you're trying to include the processes in the real atmosphere. So through sensible heat flux and latent heat flux. Like for example, clouds, like vegetation, you have a transpiration, evaporation of water. That is all, I mean, that is represented through the sensible and latent heat flux. And also you have hydrological cycle that is not, yeah, so you can also write a separate equation for this, like hydrological balance, like water cycle. So that means the precipitation rainfall, which is falling on the earth, and then it all evaporates, like through just water evaporation or through the transpiration from the plants. So evaporation is actually nothing but the transpiration plus evaporation of water bodies. So precipitation minus evaporation should be equal to zero if it is balanced, or it. So if it is not zero, then it goes through like as a runoff. So when it rains, and then immediately the water flows on the ground, then that is called runoff actually. So yeah, you can have an equation for this also. And from here, you can predict the like precipitation or hydrologic water variables. Okay, so that's, yeah, so this is kind of a more trying to represent the more reality of the atmosphere through the equations. That is what, yeah, I wanted to show from basic equation to like assumptions and to the real atmosphere, how we evolve. Yeah, this is a zonal mean temperature of the earth. I wanted to show that you see this is the zonal mean. That means this is the southern hemisphere from 90 degrees south to 90 degree north, which is average annual mean temperature, surface temperature, or surface temperature, sorry. So from surface to the whole atmospheric levels, I think the top of the atmosphere, the temperature. You see that over tropics, like India, the temperature, if you see close to the surface, it's about, yeah, like more than 20 degrees here. But whereas in the northern hemisphere and southern hemisphere here, like where I am now in Norway, southern hemisphere, like annual average temperature is like negative. See about -10, even in southern hemisphere. So that means the Earth is like, yeah. So you can imagine the complexity of on the Earth by just looking at this temperature pattern. So you need to represent this whole complexity through equations and try to predict the climate. Yeah, I wanted to tell another model to show the another equation for modeling the lateral flow of dissolved organic matter in community terrestrial system model. So why I'm showing this is because my current research work is on this. So I'm trying to work on like, so as I showed in the Earth. So if I go back to the schematic. Sorry. Okay. Oh. Maybe here. Yeah. So if you see that in the schematic, in the climate system, it's not only just the temperature or the precipitation. You need to really.
1 second, Mr. Devaraju. Audio system, I think it's not that clear. Is there an issue? Can you just rectify it if it is possible?
Okay. Is it?
Voice is not that clear. There is some lag. Cut adang barta ide.
Oh, okay. So I am on Wi-Fi, maybe. So is it from the beginning like that or only now?
No, in between it happened. Now it's okay. Now it's fine. Okay.
Okay. So yeah, I think it has to do with the Wi-Fi here, maybe sometimes.
Now it's fine. You just continue.
Okay. Yeah. Thanks.
Yeah.
So yeah, what I wanted to say was that, yeah, in the climate system means you have really a lot of processes and you need to model all of them. So currently my research work is focused on like how the like carbon, which is from the vegetation, is going to the soils, and also you have runoff, right? So the water, which is falling as rainfall and then goes to the rivers and then ultimately reaches the ocean. So how this water is carrying the carbon from the vegetation or from the soils or from the atmosphere, how that carbon is transported across the rivers and ultimately reaches the ocean. So I'm trying to model that now in an already existing Earth system model. I'm trying to incorporate this this process, like dissolved organic matter or dissolved organic carbon, how the carbon which is dissolved is transported to the oceans. So that's why I specifically choose to show that modeling. Okay, this is what I'm talking about now. Those, yeah, a brief background of dissolved organic matter. So that means dissolved organic matter is defined as the organic matter fraction in a solution that passes through a 0.45 micrometer filter. So yeah, dissolved organic matter is often quantified by its carbon content and is referred as dissolved organic carbon. So because in the water, if the chemical, it's not only just the carbon. So you have many other dissolved nitrogen, other chemical compounds. So that's why it is called generally as dissolved organic matter. But for the simplicity of the equations, we tried to model one by one, like only carbon for the, which is very important now. So yeah, I tried to model only the dissolved organic carbon. And our focus is that. So in the high latitudes, like in Europe or like higher latitudes, so the soil carbon, the carbon in the soils, actually, it's may amount to nearly like 1,500 petagrams of carbon is stored. Actually, this much carbon is stored in the highlight soils. So that means the yearly lateral flux of carbon, that means the carbon which is going through the water, that is lateral flux through the waters from soils to the running waters, is about a fifth of net ecosystem carbon exchange. So which is of about 400 teragrams of carbon per year. So this huge amount of like about fifth of the net ecosystem carbon, which is going into the water, and ultimately it is reaching the ocean. So this is a quite a big amount, big carbon. So this is a schematic that shows dissolved organic carbon flux in kg of carbon per hectare per year. This is in, I think, Amazon, somewhere in the tropical region. So the carbon from rainfall and even through fall, that is from the vegetation and also from stem flow, which is all going into the land, and this is reaching to the rivers. So yeah, so we are trying to represent this in the models. So, and for the global estimates, the terrestrial carbon inputs to inland water, like all over the globe, over the earth, it's about current estimates. These are like, so since there are not many observations exist. So, but there are some observations. With those observations and some modeling work, recently many scientists are trying to estimate this dissolved organic carbon. That is about 5.1 petagrams of carbon per year. Every year, this much of the carbon over the globe is going into the waters, the inland waters. So, of course, this number may be highly uncertain. So, just caution because of the lack of many studies or more studies. So I just put this slide here and this sentence that there are global land models which like RKD and Jules have represented already. There are some models which are already trying to implement this process and simulate the carbon, how much which is going into the water. So why I am modeling here now for Norway actually. So this is important for Norway because the dissolved organic matter linked with ocean waters is important for Norway, especially for cod spanning. So cod is a fish, actually cod fish, which is like here. It's and Norway is Norway's one of the biggest economies through fish. So its fisheries is really important here. And so this organic matter or organic carbon, which is going to the ocean from the land, terrestrial ecosystem, is really important for the spanning time of the fisheries, cod fish. So the hypothesis, this is an hypothesis. There are some studies which hypothesize that, so when you transport the organic matter or carbon into the oceans, the oceans become dark, like coastal waters or coastal oceans become darker. And then that means you have a climate warming. And then, so that is leading to the cod spanning delay, So if you observe here, so this is the figure to represent Shehi disk depth. So that means this is the disk actually. So earlier, I think way back in the previous, like old days, they used to use this disk to see the clarity of the oceans, how deep this disk can go into the water. Then they used to measure that the clarity of the water or the oceans. So you see that from 1900 until today, so the clarity of ocean waters has decreased. This is a figure for the Baltic Sea and the North Sea. So you have two dark blue and light blue. So yeah, you see that there are like, it's a really dramatic change in the clarity of the oceans, oceans water. And then if you look at also the air temperature anomaly in that region, so you see that there is warming trend. And also you see the spanning time of the fisheries. You see that the spanning time was in 1860s or 1900 was here, and now it's about like more than 20 days. It's delayed around 1990, but then it's slightly coming back. So we want to understand this process actually. So why this is happening? So we want to there are not many studies to link these processes, but there are some studies hypothesize that these may be linked. Dissolved organic carbon and the spanning time maybe is linked. So that's why I'm now working on a project called Green Blue. Green Blue means green is like vegetation or forest, which is linking forest is really affecting the oceans. Like blue is like to refer to oceans. So the carbon from the vegetation which is going into the oceans. So this is funded by Norwegian Research Council, and the project title is Terrestrial Ecosystem Change Impact on Marine Ecology. So how do we really represent this in a system models or climate models? Mathematical representation of this. So this is the again hypothetical or conceptualized network of the rivers. So you have a hill slope river you represent, and then you have sub networks. So let's say this is a catchment. This is the big river main channel, and then you have small river, like small whatever the networks or tributaries. They transport water to the main rivers, and you have hill slope. From hill slope, the water transport goes through tributaries and reaches to the main rivers, and from rivers it goes to the oceans. So this is the real network, and you conceptualize for a simplicity of the mathematical equations, you assume that there is one hill slope which is transporting the water to the sub network, like these ones, sub networks or tributaries, and then all these tributaries or sub network goes to the rivers. So that is what represented here, like channels. So you conceptualize like that, and of course you have all these processes are all represented. I'll go into details in the next session for the carbon cycle, like biogeochemistry in the land process. So there is this process already represented, and you export the carbon from this CLM, CLM means it's a community land model. So you export the carbon to the river networks, and then river transport this carbon to the oceans. So here I show a simple mass balance equation for the carbon transport. That is the rate of change in total, like let's say a control volume. Control volume, what I mean is let's say hill slope. In hill slope, how water is generated here. Okay, so that means you write a mass balance equation for the hill slope, or write another same mass balance equation for subnetwork. In subnetwork, you have a water coming from hill slope, like input or the DOC. So that is the stream flow is Q, which transport the DOC carbon. Okay, that is carbon in the water that is going in from hill slope to inside, and minus whatever is going out from subnetwork to the main channel. That's what you can inflow minus outflow. plus if there is any source already exist, like source terms, like if there is already carbon exists in the sub-tributaries, then you represent that source, or which is something which is coming from, again, adding from the forests, or carbon which is coming from or from the rain or whatever. So that's the source of the carbon. And then this is a sink term. If there is some reaction, so carbon, whatever which is goes into the river, it may not, everything may not be transported, but some carbon may be reacted to other forms. So that means there is some removal of carbon, that is DOC. So these are all the processes that you write. This is kind of a mass balance equation. The rate of change of the total storage, total storage of carbon in a subnetwork is equal to the incoming minus outgoing plus any source term or any sink term. So yeah, this is what I tried to write here in a more understandable format. So DOC, that let's say control volume. So that is V is the total volume storage, like the volume of the water here. And then DOC you have. So CV means that is the control volume here. So basically, if this is a subnetwork or even in the river main channel, then you have something coming in and going out, and there you have also some store, like some source term or sink terms. So so again, you can make a lot of assumptions and make this equation look simple and to find an analytical solution, or you can also do the numerical methods, apply numerical methods and solve the equation. So for simplicity, I try to assume some of the some processes, like assumptions, like there is no reaction between DOC. That means whatever the carbon which is going in, is everything is going out. So that means there is no reaction. Basically, assume that there is no reaction. That means you just, whatever you put in the carbon in the water, then that is going out. So assume that, that's it, assumption. And then also, so at time zero, assume that there is a DOC initial some concentration C0, and assuming no DOC present in the water. I mean, if you assume there is no DOC present in the water, then initially you can say that DOC is 0 at time 0, I think. And stream flow rate in and out same. Assume that the stream flow rate, like Q in and Q out are same. So the speed of the flow is, stream flow is same. And then you have V is the volume of water per catchment area. So so with all this assumption, this equation can be simplified to this form. And then so also assume, since we say that there is no reaction, that means whatever is coming in is going out, like DOC in, whatever, DOC out is actually whatever the DOC in. So it's a DOC, and because non-reactive, so this becomes 0. So you can solve this equation and get an analytical solution. So you have the solution like this. If DOC is
okay,
so,
continue madli.
So what is the time? Sorry, I took more time now.
Yeah, sorry for the interruption. Can continue.
No. Yeah, I can continue. Yeah, maybe I'll just another 1 or 2 slides, then we stop, and then we can start afterwards. Okay.
Okay.
Yeah. So this is the solution for the equation. And you see that how we can predict the DOC, the carbon over time. So from this equation with all the assumptions, so you can see that the concentration of DOC along the time. So if you change the outflow, the stream flow rate, you see from green to the red. If the flow rate is high, then the reaction is like quick. So the carbon which is going quickly, and if this is the stream flow, outflow is like small, the speed 5 cubic meter per second, then you have slow transport of DOC in the water. So similarly, if you have more water like stored, like V, if you increase the volume volume of the water in a network, then of course, so that DOC evolution over time is changes. Oh, yeah, basically these are with playing with different stream flow and different water storage. So you see that you get prediction of DOC over time. Okay, so I thought since I think in the previous 2 days, people, I think there's a few participants are introduced to Python. So I was thinking to give it an exercise to write a program to predict the DOC concentration from this equation actually. And then maybe we can stop here. If anyone can later come back and we can write a program if possible, and then we'll continue. So,
Okay, Mr. Devaraj, are you going to stop it now?
yeah, probably. So
for 10 minutes or 15 minutes, we'll take a break and we'll continue.
Yes, yeah, we'll do that. Okay.
Okay. Thank you. We'll continue further.
Yeah, I leave the screen like this, or what do I do? Or
we can stop it now. Again, we can log in and we can continue.
Okay. Yeah. Thanks.
Yeah. Again, we'll join and continue.
Yeah.